And I'm beginning now to segue to my introduction of our keynote speaker, in case you're wondering where I'm drifting with this. So there are climate needs then associated with the different crops that we grow. So for example, we grow things with a 30-day grow cycle. Radishes be a great example of that. So from planting to harvesting, 30 days. We also grow things that you plant and you don't get the first product for 7 or 8 years. For example, hazelnuts, but then those trees will continue to produce for decades. So we have that time frame as well. And all of those time frames need to be managed from the standpoint of the climate, and the climate that will happen decades from now, as well as the climate that happens tomorrow. So all these things are important. So weather, so the changes in weather, and being able to predict those weather changes and on a micro scale as well. So that within the farmer's field, they can predict when they're going to need to be able to make an application, harvest, plant, whatever it happens to be. But also thinking about, if I'm planting a hazelnut tree that I expect to be producing for the next 4 decades, what do I need to be thinking about in terms of climate change, in terms of what varieties I should be planting that will be able to still be productive as the climate does indeed change and as we see it changing. So within that then is this importance to be able to deal with weather, understand it, take advantage of monitoring and knowing what's going on. And that's what our keynote speaker for this morning has spent his academic career working on, so Chris Daly. So I really am pleased to have the opportunity to introduce Chris this morning. Chris is a professor in the School of Chemical, Biological, and Environmental Engineering here at Oregon State University. This is a department that I've collaborated with many of the folks in that department myself over the years, and it's a terrific school. Chris's background is pretty unique, so I've sort of set him up as a person interested in climate and in weather, and that's certainly true. He has a background in meteorology, climatology, but also has expertise in geography, ecology, and statistical modeling. So I was able to bring all those different disciplines together to think about the needs. He's actually pioneered an emerging discipline that he calls geospatial climatology. So that's the study of the spatial and temporal patterns of climate and their relationships with features on the Earth's surface. So geospatial climatology. Chris founded and directs Oregon State University's PRISM Climate Group. So this is a recognized world leader that works in this area of spatial climate analysis. So Chris, it is my pleasure to welcome you to the podium, and your title, your title of your talk, Challenges in Mapping the Nation's Climate and Weather, Every Day, Everywhere. Chris, welcome.
I have a different microphone on, so hopefully, can you hear me all? Sounds good? Okay. Well, thank you, Prakash, for inviting me to come here today. I have to say that I barely know what the word ontology means. This is something very new to me, and I expect that I'll be presenting some things that are new to you. But I think this is an interesting opportunity to kind of get a feel for the challenges that we face when we try to do mappings, both spatial and temporal mapping of weather and climate across the U.S. I think there are some parallels that you'll see. And we don't use the same terminology that you do, most likely, but we have our share of difficulties with data and metadata, and I'm going to go into some of these. And I think there'll be some eyebrow raisers when you see the difficulties that we have. As you know, we are in the throes of climate change, and there's still a lot of controversy around that, and I hope to talk to you a little bit about that today. So what I'm going to try to do is give you an introduction to who we are, so you have some basis for understanding where we're coming from, a little bit about who we serve, who our clients are, who our users are, a little bit about what we do and how we do it, and then get into some interesting challenges that we face with metadata data. And I want to end the talk with a little bit about natural language challenges that we have, which I know some of you are way better at this than we are. And you may be able to come up to me and say, yeah, that's easy, we got that solved, let me tell you how to do it. So that'd be perfect. So first of all, what is this? Anybody know what that is? Anybody? Did you see it on the news? You're exactly right. This is a microburst. This is in Phoenix, Arizona, just a short time ago, on 19th of July this year. What you're seeing here is a massive thunderstorm with an anvil cloud that we call on top, and you can see it right here. And what you're seeing down below is basically a nuclear explosion in reverse. You can see the outflow diverging out, screaming along and dumping copious amounts of rain in the area. And this is a map of Phoenix, Arizona. You can see these little triangles here are weather stations that we have. So Phoenix is considered a well-instrumented city. Of course, there's where the thunderstorm hit, and there's nothing there. So it must have been a lot of rain here, but we have no idea how much. And this is a typical problem that we have. This is the story of our lives. Every time we want to know what's going on, there's nobody there to measure it. So keep that in mind as we go along. So a little bit about us. I have an applied research team. We're totally on soft money, so we have mostly federal contracts that we work with. I'd say the U.S. Department of Agriculture is our largest funder. NOAA, the National Oceanic Atmospheric Administration, probably be in second place. We're housed within a group called the Northwest Alliance for Computational Science and Engineering, or NACS. It's kind of hard to say. For about 20 years, we've been the climate mapping center for the USDA. We produce all of their climate maps, and we've become the de facto climate mapping center for the entire country. And just to give you an idea of some of the thrusts of the things that we do, we have probably our bread and butter is the way we started was mapping long-term baseline climatology. Now, until we came along in the early 1990s, all of the official weather maps, the precipitation maps, temperature maps that denoted 30-year average long-term climate were all done by hand. They're all hand-drawn by expert climatologists at tremendous expense and time. It usually would take maybe 2 to 4 years to develop one of these maps and about maybe $250,000. So when we came along in the 1990s, the last maps had been done in the 1960s and no one wanted to do them again. It was just too much of a pain, costs rise, no one wants to do it. So we became, my job was to try to develop a computerized way of doing these maps much more quickly and easily. And you can see that we have just a huge number of departments within the federal government that use these maps. So climate and weather cut across just about every single discipline you can imagine. That's a problem. That can be a plus and a minus for funding, by the way, because no one agency wants to step up and give you the money. It's like, why should I do it? Everyone else needs this data too. So everyone kind of stands back and waits for the other to act. We also have, we work with a risk management agency. This is an agency within the USDA that most have never heard of, the RMA, but they're the ones that oversee the federal crop insurance program, which is run by private companies, but they oversee it. And we're talking about $150 billion of crop value insured every year and billions of dollars of taxpayer money spent to pay crop loss claims. And I'll talk about that a little bit more as we go through. And we now provide the weather and climate information for that crop insurance program. Previously, they had used Weather Underground or whatever they could find to try to determine whether a claim should be paid. And they're playing around with billions of dollars of our money, and this is not a good thing. So now they have an official way of looking up climate and weather data. We also are starting to get into what's called underwriting, crop insurance underwriting, which is how do we get agricultural producers to engage in less risky behavior. So they don't plant too early, they don't plant too late, they harvest on time, and they can lower the risk. Based on climate information that we have, we can tell them what the risk is of a late spring freeze, for example. So you don't want to plant too early because you're going to be at a high risk of a late spring freeze. And so we're starting to help them reestablish some of their guidelines for getting crop insurance in the first place. We're also on the right-hand side here, we've been involved for a number of years with the Department of Energy doing biofuel resource mapping. So this is where we take our climate data and we've developed some fairly straightforward, fairly simple crop models that allow us to determine the potential ranges of new species of crops that aren't typically grown in the US. And this is for the bioeconomy. So these would be feedstocks such as switchgrass, energy cane, biomass sorghum, some of these crops that would be grown specifically to be put into biorefineries to produce ethanol. So we've been working on these maps for quite a number of years. So we have a public data portal, which is prism.oregonstate.edu, and we provide this. The RMA allows us to provide kind of lower resolution climate grids to the general public through a website. And we're finding that more and more people use geographic information systems, or GIS, or some other spatially driven software to do their analyses and decision making. Everything seems to be becoming map-based, and Google has really pushed that forward with Google Maps and such. And they all need gridded wall-to-wall climate information and weather information. And so we found that the popularity of the site has just gone through the roof. We're talking about, over the last couple of years, 70 million Prism grids have been downloaded from our site. It's really pretty amazing. And the range of applications is staggering as well. People are using the data for things I never could have thought of. Retailers use the data to determine when they should start selling flip-flops instead of closed-toed shoes, or when ice cream ought to be put on the front shelf, as well as kind of the ones you would expect, you know, agriculture, hydrology, ecology, things like this. So it's really pretty amazing to see the wide range of uses of our climate and weather data. So first of all, what the heck is PRISM? Is that just a name? Is it an acronym? What is it? Well, it's an acronym. Excuse me, it's an acronym. It stands for Parameter Elevation Regressions and Independent Slopes Model. Now that you heard it, you can forget it and just call it PRISM. But the idea again is that we have, if you were to take, for example, all the weather station, all the, let's say the rain gauges that are on routine networks across the country and put them into one place, it would probably not even fill up this room. So the actual land area that's being covered by weather station observations is extremely small. And what you need are ways to interpolate that or extrapolate that information to places where we don't have any information. And that's what PRISM is all about. And so we have a grid, regular grid set up across the conterminous US. Each pixel is about a half mile by a half mile. And we make estimates of what the weather and climate will be. I use the term weather and also climate, as you notice. So weather is what we see from day to day, and climate are long-term statistics. Let's say 10 to 30 years of information, and some statistic like an average or extremes that may occur. Excuse me. And we produce both maps. You'll see we produce both weather and climate maps for our users. So a little bit about how the model works. Just a very light touch. I promise it won't be in the weeds too far. What I'm trying to do is take the process an expert climatologist would use to develop a weather map, but do it a lot more quickly and a lot more objectively. What we found with a lot of the hand-drawn maps is that they would have a lot of detail in places where they knew the climate well and very little detail in places where they didn't know it well. And so you end up with these maps that have kind of a variable resolution to them. PRISM says, look, I'm going to do the same thing in every pixel. Every half-mile pixel, I'm going to do the same thing. And so what we do is that we have a little regression function that runs pixel by pixel, goes through the whole map, looks at stations that are nearby in that local area, and develops a relationship between, if we're doing long-term climatology, it would be elevation and temperature and elevation and precipitation, for example. We also, for weather maps, we might use the long-term climatology as a predictor grid, and I'll talk about that in a minute, or even a radar map, radar reflectance. This example here is in the Qinling Mountains in east central China, where we've done a lot of work for the Willamette Valley grass seed growers as they try to develop markets, export markets to China. We needed to find out where their grass seed could grow well and where it would not grow well in China. And so we mapped the climate there in a great amount of detail. Now, the real meat of the model is that it weights these stations coming in based on how similar physiographically they are to the pixel that we're modeling. And this was something that made PRISM unique back in the 1990s. So obviously, if you're at a pixel and you have stations that are close to you, you want to weight those more highly. Stations that are a similar elevation, yeah, okay, you probably want to weight them more highly. And then we get into more interesting stuff. And these grids that PRISM uses, it's a very what we call a rich data environment. So PRISM knows a lot about the Earth's physiography. We have grids that define terrain orientation. So if you're on the windward side of a mountain range where it's wet, and you have a leeward side of the mountain range where it's dry, you want to make sure to separate those two out and reject stations that are on the wrong side of the hill. We also have terrain profiles. Mountains that are high tend to cause a lot of orographic uplift and amplification of rainfall and snowfall. If you have very gentle terrain, they do very little, and so we have to be able to stratify for that as well. As you know, along the west coast here, we have a tremendous temperature gradient from the coast to the interior. On average, for example, the high temperature on the coast of Oregon during July is about 65 degrees. Here it's about 85 degrees. So we have models that go through and determine how susceptible to the coastal environment the pixel is. And we also have the ability to look at temperature inversions. Down in the valley here in the wintertime, for example, we get these awful fogs. We get these valley fogs where all the cold air settles down into the valley bottom, and it can be 35 degrees down here, and up at 4,000 feet in the coast range, it can be 65 degrees. So we have to be able to determine where in the terrain we are, whether we're in a valley bottom or a ridgetop. So PRISM is able to say, look, what stations do I have that are similar in physiography to the pixel that I'm looking at this moment? And this is where geospatial climatology comes in that Dan Art mentioned. This is where we're bringing in a lot of information about geography, if you will, to be able to interpolate climate. So here's what the mean annual precipitation map for Oregon looks like. And you're thinking right away, wow, this is like a tale of two states. So the cool colors here on the left are high rainfall, and the warm colors on the right are low rainfall. And what you see is that we have two terrain barriers. We have the Coast Range, which is where the most rainfall occurs. And then we have, believe it or not, we're in a rain shadow right here in the Willamette Valley. Corvallis is right in here. And then we have the Cascade Mountains. And once you go over to the Cascade Mountains and we'll go over to the east side, you're really into desert areas. And so we have a Western Oregon, Eastern Oregon, the vegetation is very different. We have a very wet, well-watered condition in the west and a semi-arid condition in the east. So this is a very challenging place this is actually where I developed PRISM, first developed PRISM. So it's best to develop your new models in the most challenging place you can find. And here it was in my very backyard. So that was great. And we're going to look just briefly here at Santiam Pass. So Santiam Pass is a pass in the Cascades. As you drive over the pass and down to the east side, the mean annual rainfall is decreasing by about 1/100 of an inch per car length as you drive down the road. So it's happening really fast. And it's very challenging to try to reproduce that gradient. So what I'm showing you here is that we've got, we're running PRISM just on the west side of that pass where it's wet. And we have an elevation versus precipitation relationship here. And we're coming up with about 2,100 millimeters. So we're looking at 80, 90 inches per year, somewhere in there. Now all we have to do is move to a pixel that's just a few kilometers to the east, which I'm going to do now. And all of a sudden, I'll just go back and forth here. You can see that the regression function is completely sliding down to the east side condition. It's rejecting those stations on the west side. So this is topographic facet or hill slope weighting that PRISM is using. And you're able then to reproduce these gradients. If you just simply looked at distance alone, these wet stations would overwhelm the dry stations, you know, with kind of some blob, you know, prediction in the middle somewhere that wouldn't be very good. This is an example of coastal proximity that I was talking about. This is the San Francisco Bay Area. And you can see that we've got all these cool colors here. This is where air parcels can get into the terrain, get into inland areas fairly easily. And then the warm colors are where these parcels have a hard time getting in. And we have a pre-processing model that goes through and defines these zones. So along the coast, for example, PRISM will look up and down the coastline for stations similar to that coastal pixel's proximity to find the precipitation or temperature elevation relationship. It won't look into the interior or reject all those stations. So again, physiographic weighting. Just north of the Bay Area, this is in northwestern California. This is where you can see a lot of temperature inversions. You can see these cold pools that lie down in the valleys, these cooler colors. And then you have these warm colors that are up in the mountain ranges. And it's no accident that the tree fruit is grown down in the lower areas where they need a certain amount of chilling hours to be able to produce good flowering conditions in the springtime. And the grapes are grown up in the upland areas where they don't need that. So this is where we get into these microclimatic situations. If we want good climate grids that agriculture can use, you have to get down to this really fine level of detail. So another map that we've done for the USDA is one that you might have heard of. If you're a gardener, we have a lot of gardeners here. Yeah, the USDA plant hardiness map. Anyone who's used this map? Maybe some of you? Yeah, so this is a map that is this is probably the most well-used climate map on the face of the earth. I think I can safely say that. And it basically says, how cold will an average winter get at my location? So what's the lowest minimum temperature of the year averaged over the last 30 years? And each perennial plant that you buy at the nursery or at the grocery store is rated by a plant hardiness zone. It'll say this plant is hardy to zone 7A. And that has a certain temperature range adapted to it. And you know what, you can go here to this website and you can determine what your zone is. And you can find out whether the perennial plant that you're buying will survive a typical winter at your location. And this gets about 500,000 visits per month. It kind of spikes during the springtime, as you might expect, and then it comes down in the fall a little bit. This is through a cooperative agreement we have with this USDA ARS, which is Agricultural Research Service. They're the ones that have traditionally been the owners of this map. And for the first time in 2012, we actually produced a digital version that is online. Before that, they were mostly hand-drawn maps, so we've really come a long ways. Something else you may not be aware of, I'm sure you're not, and that is that the PRISM climate grids, which describe the normal conditions and patterns across the Earth's surface, are used when you look at your forecasts from the Weather Service or from the Weather Channel, for example. They use the PRISM grids to determine what the normal conditions are, and then they overlay their forecasts of how those conditions may deviate from that long-term average. And that's what you see in your forecast. They take the PRISM grids and they take the anomaly forecast and they come up with what the temperature is going to be today. Before the Weather Channel started using our data, they were predicting temperatures in the mid-80s on the Oregon coast, which is correct for the Willamette Valley, but not for the coast. And the coastal people there were laughing at them going, this is worthless, this is no good. The temperature never gets 85 degrees in the summertime over here. What are you thinking? But once they started using the PRISM data, they came down and they were producing 65-degree temperatures instead of 85. So now these long-term climate maps are really useful to us when we want to map weather. At day-to-day, weather stations come in and out. Sometimes we have a lot, sometimes we have just a little. And we wanted to find a method that was very robust to a varying number of weather stations coming in and out of our maps. And we find that the best way to do that is the same way the forecasters do. We use the long-term averages as our first guess, and then we assimilate whatever data we have to make changes to that first guess. So instead of using elevation as our predictor, we're now using the long-term climatology. And an example here is that the long-term average maximum temperature in July for the Colorado Rockies is a little bit small here. You can see the mountains sticking up in the cool colors. That's where it's cooler. In 2003, this was the hottest July on record. And all the colors are warmer, but the pattern's the same. It's just the deviation on that long-term pattern. So we use this method called climatologically aided interpolation to do our weather maps from day to day. So we produce maps. We have monthly maps going back to 1895, and we have daily maps every day starting in January 1st, 1981. So we have a fairly long history of both daily and monthly maps. Now, climatologically aided interpolation doesn't work all the time. Out in the east of the Rockies, is flat. This climate doesn't vary much. There's really not much predictive capability. And those of you that live east of the Rockies know that during the summer you get these big thunderstorms. They're very stochastic, they're very random. Climatology is not going to really tell you where they're going to pop up from day to day. But we have radar. And a lot of you have seen radar images and animations on television as storms run through. You can see where things are. Radar doesn't give you a good idea of how much rain fell, but it tells you where it fell. And so we assimilate radar information in with our rain gauge data to produce a combination. So for example, I just have a small example here. This is an area back in 2003 where we had a lot of data. This is actually Arkansas right here, and Memphis, Tennessee is here. So this is a state, a small state of Arkansas. And it looks like we've got a pretty good handle on where the rainfall is using the station data. You can see it right here, a big blob of rainfall, and you can see areas where there's no rain. But when you bring in radar, you find out that you were really dead wrong. You weren't even close. This is what the actual detail was actually like. These are all rain cells. These are thunderstorm cells that were popping up. And so we made this into this. Thank goodness we have radar east of the Rockies, because otherwise we'd be really very, very wrong if we were to try to determine how much rain fell on any given field, let's say, for crop insurance. So just a little bit about crop insurance support, just a brief idea of what we were asked to do. So we really needed to ask 3 questions. So the crop insurance adjuster gets a claim in the door. And the first thing he has to do is figure out whether the actual event that the farmer said he had that damaged his crop occurred. Did it even occur? Was there a hail event? Was there heavy rain? Was there a drought? Was it a late freeze that froze the crop? What was it? That happened. And then the second question is, well, okay, it happened, but was it unusual enough to warrant a claim payment? If you were expecting something like this to occur, that's your problem. But if it was something truly unusual, then we'll pay your claim. And so you need the long-term climatic context to do this. You need both weather and climate to make this work. And we wanted to make this process very quick and easy, and so we have a web portal. And the NACS group that I work with is a pioneer in usability engineering in terms of creating websites that are very, very easy to use for people that aren't very sophisticated computer users, and crop insurance adjusters are in that category. They can turn the computer on, they can use a web browser, and that's pretty much where they are. These are ag folks. So this is just a quick example of one thing we have on our website. You can go, it's called a summary assessment. You can go to a location and you can specify a time period and say, what was it like then? Tell me overall what it was like. And what we show them, this was actually during the 2010 tobacco growing season in Raleigh, North Carolina, which is April to November 2010. And immediately they get a feel for, wow, okay, this is rainfall. Yeah, that's pretty typical. And then we have red, red, red. So the mean temperature, the max temperature, and min temperature are all really, really warm. And so they immediately can see that this was an unusual situation. Now down below we have a table that describes in quantitative terms that the precipitation was 95% of normal, okay. The temperature was about 2.5 degrees above normal Fahrenheit. And so the question comes up, is that a lot? Is that a little? 2.5 degrees doesn't sound like much. I mean, that's not much. Well, as it turns out, if you were to rank that period with the same period over the last 30 years, it was the warmest period in the last 30 years. It got 1 out of 30. And what we do is we're able to then use a little ontology of our own and I worked with climatologists across the country in different states to come up with this, that we use a ranking. So the middle 40% of the distribution of these 30 events is considered typical. We don't use normal, by the way, because that is a very specific term that we use for a 30-year average that moves forward every 30 years. So right now we're in the 1981 through 2010 normal period is what's being used as baseline, and then 10 years from now, or in 2020, we'll move up 10 years. So we don't use the term normal. But typical is what we use. And then we go 71 through 90% is wet and warm, and then 91 to 100 would be unusually wet or warm, and the same on the cool side. And this vocabulary allows the adjuster to go to the farmer and say, you know what, this event was typical for your farm. And the farmer goes, okay, you know, I can't argue with this. You guys got me nailed. Or they come across and say, you know, you were in North Carolina and your crop growing season was unusually warm, and we're going to pay that claim. And these terms work a lot better than numbers. If you were to say you were in the 75th percentile, I'd say, well, so what? So this is a way that we're trying to categorize the weather so they can speak about it to the farmers. So far I've been skirting around the issue that I'm really going to spend a lot of time on here, and that's station data. Garbage in, garbage out. If we have bad station data coming in, we're going to get bad results coming out. So our challenge is to walk the line between numbers and quality. So there are a lot of backyard weather stations out there, thousands and thousands of them. We don't use any of those because we don't know how they're doing their measurements. We don't know what the protocol is. Some are on their rooftop, some are in their backyard under a tree. We don't know what's going on. So we use ones that we can learn about and accept. And so we use NOAA's major networks, the Forest Service, Bureau Rec, U.S. Department of Agriculture as a network. Also, one I'll mention again is the Corvallis Precipitation Network. This is a funny name. This is the largest volunteer precip network in the country right now. And we have a lot of state and regional networks and also agricultural mesonets. And so we have a lot of, we have networks coming in, new ones coming in all the time. And of course, they all have different data formats. They all have different weaknesses. They have different flags for quality. They're all different. And of course, they like to change things on you without saying anything. And so we're constantly having our feeds break and have to redo them. So I have a couple of guys in the office who spend almost all their time on data assimilation. This is a big, big deal, and we spend a lot of time doing it. This is an example of the data density for precipitation that we have in the east side of the US. You can see a lot of the urban areas are very dense, and some of the areas out in the country are much sparser, as you might expect. This is what the west looks like. The poor state of Nevada is always gets short shrift. There's literally nobody there, so no one cares. But they do, they do. Anyway, so I want to pick on one particular network, and this network is really important to the U.S. It's called the National Weather Service Cooperative Observer Program, CO-OP program. We love this program. This program has been around for at least 100 years. And they've been measuring precipitation and temperature pretty much in the same way for that last 100 years. And so this is what's used to determine how the climate has changed in this country over the past 100 years. So you hear climate change deniers, climate change proponents saying, well, it's been warming up. Other people say, oh, it's been cooling down. This is where the data comes from. Once you get back before the 1980s, before automated stations, this was really the only network available. So it's worth spending a little time to see just how they measurements are made and what the pitfalls are in these measurements. It's kind of interesting. So they take precipitation and maximum minimum temperature every 24 hours at this, hopefully the same time each day. But the time of observation varies. These are volunteers. They don't get paid to do this. And most of them either take an observation early in the morning, 7, 8 a.m., maybe 6 a.m., and then there's a bunch that take them in the afternoon, maybe at 4 or 5 or 6 p.m. This causes terrible headaches, and I'll talk about this in a minute. Like I mentioned, these are all done by volunteers, which is both good and bad. It's good in that it's cheap. The federal government, despite the importance of this program, puts very little money into this, a few million a year, which doesn't really cover expenses. And it's bad because volunteers are volunteers. How can you force them to do something they don't want to do when they're volunteering? They'll just say, I quit. And then you have to back away and say, okay, you don't need to do that. So it's an interesting balancing act. The first problem we have with co-op data is that we often don't even know where the stations are. When you have an 800-meter grid cell and you don't know where the station is to the nearest few miles, you're in real trouble. And we have this problem a lot. This is an example of a paper I have in preparation with some collaborators at the Coweta watershed in North Carolina. And this is a little hard to see, but there are 3 co-op stations here. One's in red, and one's in yellow, and one's in orange. And these are the various places that various sources of metadata have placed these stations. And this is a 1 kilometer bar, by the way, from here to here. And so the main station at the Coweta is actually right here. This is the main headquarters station. It's been placed as far away as about 7 or 8 kilometers outside the watershed. And lately, it's been, in 2009, the National Climatic Data Center put it over here. Sometimes this is because of imprecise location. They'll locate it to the nearest 1-minute latitude, longitude. And sometimes you'll find that, in fact, the yellow and the orange stations were actually located in the same place for many years because of this rounding and truncating of information. We also find that back in the early days, they would locate a station by saying, you take road 54, you take your first left, you go up the hill about half a mile and turn right. You know, that's where the station is. And then they would look at some type of map they would have to try to figure out what a latitude longitude is, and boy, is there a lot of error there. Today, we have GPS. A lot of these stations have been GPSed, but the locations are often still wrong, and it amazes me that we don't really know where these stations are. So that's a big problem with our locational metadata. So let's talk about people and how they make observations. Oh, you gotta love people. So out in Corvallis, this is the Corvallis Hislop official site for Corvallis, which is out on the Highway 20, off the Highway 20 between here and Albany. And Richard Maddox, back when I took this, he was the co-op observer. And here is the standard rain gauge. It's 8 inches across. It's got a little funnel in it. And he sticks a ruler in it that looks like this. And he measures how far the water sticks to the ruler. So wherever this ruler, the water sticks to the ruler, that's what he does. And those rulers, some of them don't work very well, and sometimes the water just rolls right off of it. Other times it sticks nicely. So he actually uses one that he got like 50 years ago from somebody else that says works best, because the new ones don't work at all. So they're too slick and the water just rolls off. Really stupid way to measure rainfall, actually. But anyway, you can see that the tick marks, every 100th of an inch is a tick mark, and there's a little bigger tick mark at 5/100ths, and then a big labeled one at 10/100ths, and the same thing at 0.2, 0.3, and so on. So keep that in mind. So if you do some long-term statistics on daily rainfall, this is a station in Oklahoma, you get what's called a gamma distribution. That is, this is the rainfall amount in hundredths of inches times 100 here, so this is 0.2, 0.4, 0.6, 0.8. And this is the frequency, percent of days that you get that rainfall. So there's a lot more days with 100th of an inch than there are with a 10th of an inch, right? Everything comes down like this, and it's a very steep curve. And this is a nice station. You can see that we have a nice relationship here. By the time you get out to the higher precipitation amounts, the frequency is really, really small. Makes sense. This is a nearby station in Oklahoma that has some problems, big problems. So I wrote a paper on this in 2007, which the government largely ignored because it's very embarrassing. We have two problems. We have what's called an underreporting bias, which is there's not enough frequency of low precipitation amounts, either because the observer didn't think it rained and didn't bother to check, or that ruler just couldn't pick up something that was really small, like a 1 or 200ths of an inch. And then they rounded to the nearest 5 and 10/100ths of an inch. You see these spikes sticking up in the frequency distribution. They're just rounding. And so now we've got a precision problem right away. And this happens, I'd say, in probably 75% of all the cooperative stations across the country. So this is a really, really well-known problem that we can't do a lot about. Now, it gets worse because the amount of underreporting and 510 bias changes over time, either because you get a new observer or the observer learns more or gets lazy. Any of those things are possible over time. So here's two stations. These are in Eastern Oregon, Malheur and Vail. You probably have learned about the Malheur Wildlife Refuge. So that's where that station is in the news last winter. And what we have here is 1974 to present, about 2005 or so actually, and the percent of days that are wet. And this is a statistic that agriculturists used a lot. How many wet days do we have? At least 100th of an inch in a year. And at Malheur, it looks like it's been going up from about maybe 18% up to about 25%. At Vail, it's been going down quite a lot from about 18% down to about 12%. And we look here, and this is the average rainfall on a wet day. It looks like in Vail that the intensity of an average day's rainfall has doubled over the last 30, 40 years. At Malheur, it looks like it's actually gone down a bit. So these are stations that are very close to each other. So which one do you think is biased and which one is unbiased? Any guesses? Which one do you think is biased, the red or the blue? Huh? Red? Anybody else? It's the red one. So one of the climate change predictions is that we're going to get more intense rainfall. And Vail would demonstrate that, but it would be wrong. Okay, so this is where you can get in real trouble if you don't understand the data, and be very careful about how you use it. Temperature, oh boy, temperature, okay. So for the past 100 years, this is the way temperature has been measured. There are these mercury and alcohol thermometers, and they have little weights in them. And you notice this, the top one is the minimum thermometer, and the bottom one's the maximum thermometer. And what happens is that they're tilted a bit each way so that the weight, as the temperature drops at night, the weight is dragged down. There's a little weight in here that is dragged down with the alcohol. And it can only move one direction easily. And so by the time it reaches the minimum temperature, it stops and gets stuck there. And the maximum temperature is dragged downwards to the max temperature and then gets stuck there. And you have to shake them to dislodge the weights. So when the observer comes out at their observation time, they can look to see what the maximum temperature was over the past 24 hours. So this is an example of a long-term observer. He's 101 years old. He's got the 84-year record in New York. So there he is looking at his maximum thermometers in his white box here, which is actually a very good sun shelter. So we don't actually know what the obs time is lots of times, and this creates a little bit of an issue I'll talk about. Some people don't tell the truth about their observation time, and we get spatial and temporal errors that result from this. And I'll explain why. Here's a prism map for the daily max temperature on the 31st of January 1985. Look at this big blob here. So there's a cold front that's coming down from north to south. It's an Arctic blast that's coming down east of the Rockies. And it's starting to get cold, and we have these two outliers sitting out way in front of everybody, so clearly causing an anomaly in our map. Why is that? It's because of what we call time shifting, and that is that we have a morning observer and an afternoon observer, and the morning observer was observing this drop in Tmax earlier, one day earlier than the afternoon observer, most likely because he said, look, I'm observing at 7 a.m., but I know that Tmax occurred yesterday, so I'm going to put it on yesterday's Tmax. You don't do that. You have to, you may not know this, but for example, in Corvallis, anytime there's a co-op station that has a morning observation time, the record high temperature you're looking at for today, for example, actually occurred yesterday, because it's a 24-hour maximum temperature. Now, if you're like me, the human mind wants to just kind of shift these, right? So we can see what they look like when they're the getter. It's like, come on, please, do it, do it. So I'm going to do it. A little hard to see because they're both translucent. But now we can line them up, and they look pretty close, right? Well, not completely. There are some issues here. These are really hard to see. But right here, in this particular situation, the afternoon observer never measured a real significant drop in temperature, over 17 degrees Celsius difference on that day. Here, it delayed the onset of that cold front by about 14 degrees. This creates a long-term bias in the temperature record. Now, you're thinking, how does this happen? Okay, so I'll go through the process. Let's say you're an afternoon observer at 5 p.m. Yesterday, the high temperature was 85 degrees. So you went out at 5 p.m., which is about the time of the max temperature, recorded 85. You went back in the house. The thermometer went right back up to 85 because it's still about the time of Tmax. You come out 24 hours later, and that day the high temperature was only 75. But what does your maximum thermometer show? 85, because it went right back up as soon as you took the measurement the day before. The next day comes along, temperature goes back up to 85, you record 85. The 75 is gone. The 75 was never recorded. You bridged right over it. And this is what happens. You can get a warm temperature bias for maximum temperature if you're an afternoon observer, and the opposite is true if you're a morning observer for Tmin. The minimum temperature can get bridged as well, and it looks too cold because you have more opportunity to get the cold temperature. And in this particular situation, just these two discrepancies will cause a monthly bias of 1 degree Celsius. Now you say, okay, well, it probably wouldn't show up on a map of a monthly average maximum temperature. The problem is that the observation times in this country have been changing over the century. And for example, afternoon observers maxed out in the mid-70s and then have declined tremendously, while the morning observers have taken over. This has created a cold bias in our co-op record. because we have more morning observers now than afternoon observers. And so the National Climatic Data Center has gone through and tried to estimate this bias and to take it out of the record. And they got hammered over the head by climate change deniers saying, you can't mess with the data, you can't mess with the data, you're making up data. And the answer is, well, if you don't do it, you're going to be really wrong. So this is where the climate record gets a little fuzzy. Now you also may notice that I have another line labeled here called unknown. Before the 1948 digitation, where we really started digitizing a lot of data, we don't really know what the time of observation is. And even today, there's quite a number of stations, probably 1,000, that we don't know what the measurement time is. And as you can see, we really need to know what this is. And so we've been going through on a multi-year program to actually go through observation forms. Here's an observation forms for a crop observer in June 1910. And once a month, they would collect this information and send it into the Weather Bureau. Back then, it was the Weather Bureau rather than the Weather Service. And the observation time sometimes is there, sometimes it's not. I picked out some really ones you can see very clearly, and this says 6 p.m. Sometimes it's blank. Sometimes they scratch it in and you can't read it. Sometimes the form is unreadable completely. But the neat thing about having handwritten forms is that they make little notes and little crossouts, and you can kind of get a feel for which observers are very careful and which ones are just messy and unreliable. And also, if there's some really unusual precipitation or temperature reading, they might put a little note saying, yes, this really happened. This was a terrible snowstorm. You know, I saw it, I was there. And that's good, but it's very qualitative and hard to categorize. This is one from June 1980 in Corvallis, so we're getting up into things now. And it says 8A. We tried to use optical character recognition for this stuff and couldn't do it because the forms vary. There's hundreds of different types of forms, and you can't read it very well. So what did we do? We used students. And my own daughter was involved in this, and she said, I'd rather carry rocks than read these damn forms. And so they all quit on us, and now we're having to finish up ourselves. Because we're going through about 1 million forms manually to try to do this over a period of years. One thing, now these are done, most of them are done on the web. And now it's very cleaned and pressed and nice, but there's no notes. There's no indication of how clear the observer was making his record and how unsure he was about it. So we've lost a lot by having this be nice and clean and web-based, computerized. Even though it's quantitative, we've lost that ability to really see what's going on. So there is a loss by going from handwritten to web-based, digitized. So I'll leave you with one other thing. I have just a few minutes left. One of the things that we have to do for crop insurance adjusters is look at hail. Hail is probably the single most damaging weather event for crops. We get a lot of hail reports. So we have NOAA hail grids that are estimated based on radar signatures. They estimate the size of hail. But what you'd really like is to have some ground reports also, these little red, black triangles, that would substantiate that, yes, we actually saw it on the ground. And these are often done by trained weather spotters and also by COCORAS, which I mentioned is this volunteer precipitation observation network. But they have an option of creating a hail report on the web. But many of them don't bother to do that, no matter how many times we tell them to do it. And instead, they just put it in their morning observation remarks. We have a remarks section. And this is where I need your help. So we're trying, and there's a lot of remarks with hail in them. And we would like to mine this information to be able to kind of beef up the number of ground reports that we have for substantiation. So here's some ones that are positive. Hail, these are remarks that have hail in them. Okay. Some corn pellet-sized hail and windy yesterday morning. Okay, good. We got corn size. We can figure out what that is. Mung bean-sized hail must be a farmer. Okay. Dippin' Dot-sized hail. That one I'd never heard of before. But we know how big Dippin' Dots are. Baseball-sized hail. Many windows blown out. Severe structural damage. Okay, even says when the hailstorm began and ended. That's great. That's perfect. Hail up to 2.33 inches. I was unable to find the ones with my blood on them. I had to put on a motorcycle helmet after I was attacked. As of 0702, I'm still bleeding. Okay, good. Okay, then we have ones that have hail when we pull out the text that didn't have any hail. Okay, did not have any rain, sleet, hail, or snow at our house this day. Neither rain nor hail, sleet nor snow, just plain cold. Trace of frost in the rain gauge and on the hail pad. Kokoras, some of them have foil-covered styrofoam pads, so you can actually record the size distribution of hail. He didn't have any hail. Little white balls, but not hail. He was probably recording grapple. Okay, then we have what I call the misdirections. These are tough. I got a lot of pea-sized hail, but some areas in San Antonio got golf ball and softball size hail. So he mentions 3 different sizes, but only one applies to that location, because we need to be able to geolocate where the hail was. This one I hate. On the afternoon, I ran into pea-sized hail several times on a trip from Princeton, Missouri, back to Gallatin, most noticeably in Trenton, Missouri. Also saw small hail in North Gallatin around 3:30 that afternoon. My wife noticed a trace of hail at home, but didn't see any hail. There was nothing in the gauge at observation time. Nothing. All that was for nothing. And finally, looks like here we go again. The Weather Service issued a severe thunderstorm watch, includes hail over golf ball size. We'll see. So far, they've been batting 0. So again, nothing. They mention the size and they mention hail, which we can pull out, but there's actually no hail at the station. These are tough. And I hope you guys can tell us how we can fix this. Okay, just to wrap up, my time is about up. Just some things to think about. Wall-to-wall weather and climate surfaces are accessed by thousands of users every day for a lot of the uses that I've shown you. A lot of decisions and a lot of taxpayer money depends on these surfaces. So we really need to do as well as we can. And they also, as I showed with the co-op observing network, they're used to assess how this country's climate is changing, which is a big deal. You need to have a lot of domain knowledge to create these maps. You need to be a geospatial climatologist to do a good job. And what PRISM tries to do is simulate what an expert climatologist would do in drawing these maps. And we're using what I call a data-rich environment. I don't know if you'd call it big data, but it's a data-rich environment where we have the Earth's physiography, we have the climate fingerprint, and we have radar. And we're looking at using satellite imagery as well to try to help produce better weather maps. Data are imperfect and lacking. And a lot of these observers, there's a lot of automated stations out there, which I haven't talked at all about today because there's no time, but people have their own biases and they often don't follow directions. Volunteers are just that. The Kokoras network is also a volunteer network. And they can do whatever they want because you're not paying them. There's no expectation of quality or consistency in their observations. Metadata, same problem. Station locations, this is a terrible problem that we have. And the observation times are unknown or incorrect or different. And this all makes for the difficult time in sorting this stuff out. But the data can tell you a lot of wonderful things if you can separate that wheat from the chaff. And that's, I think a lot of you would understand that. And so I think you'd also understand that to succeed in this work, you have to really love data. You have to love the data. So thank you. Whip. Yep. I think we have time for questions. He's got a mic back there. Is it on? I can't hear it.
He's going to switch it on.
There we go.
Thank you, Chris, for an excellent talk. And now for the audience, I think now you know if you go 15, 20, 30 miles up, how climate change and weather change and can swing your moods from day to day, and it does affect your life too. And right, and if you scale it up for over a number of years and number of months, you can start looking not only from the perspective of how the crop insurance and agriculture and food is produced, or how the water reservoirs are filled, or a drought or stress-like conditions are happening, but it also starts affecting how the humans are healthy, how our habitats are healthy, and what kind of interactions are happening, what kind of diseases are more prevalent because of the climate change that is happening, or weather patterns that are changing from day to day. You can imagine 8 months of a year with Oregon getting lots of rain in this part of the town, of the world. We have lots of vitamin D deficiencies, right? So allergies, diseases, cancer prevalence, and things like that. I'm not just making it up kind of things, right? But those are all tracked back to the contextual relationship of the medicine research work that many of you are working on, is how to connect back to these kinds of systems biology. So I just want to open up a forum over here for thinking about it, and that was the main reason of bringing Chris into the conversation here as a keynote speaker for here. So thanks, Chris, and I'll leave it for the questions.
Okay. Yeah, I have a question. Like, I was kind of shocked that we have so much technology. We have GPS, we know where our cars are, but we don't know where our weather stations are. So I'm just wondering, how much would it cost to basically have fully automated GPS stations that would basically send the measurement of temperature and precipitation every hour? Like, it can't be that expensive, especially if you mass produce them. And so I also want to know, like, in comparison to other countries, do they have the same, like, imprecise volunteer system? Because I'm thinking, if you invest the money once in it, it will work forever. So it will be, in the effect, save money. And why is it still, like, accepted that we have all these mistakes, even though you have the technology to fix that easily?
Actually, we don't have the technology to fix it easily. That's the problem. I didn't get a chance to talk about automated stations at all, but they need a tremendous amount of maintenance. And as you know, government funding likes to start new things, but does not like to maintain things. And so what happens is you build up a network, you have a certain number of stations, you have to maintain them with a certain amount of dollars each year. And so as you add to that network and build it up, the costs rise exponentially, and they give you a flat line. And so what happens is that the network starts to fall apart. Actually, over the years, if we were to have an automated system, we would not have been able to trust the co-op type measurements over the last century, because there's drifting, there's breakage, there's all kinds of issues with electronic systems. They're great and they can be cheap, but they do not last very long, and they need a lot of TLC and a lot of quality control. So they have their own set of problems. And so we're very happy that we had a volunteer stable network using very simple, basic methods of measuring temperature and rainfall. Now, the part that is important to what you mentioned is that there has been a move to upgrade the co-op network to automated systems to allow the data to come in every 5-10 minutes, because daily data is not useful for a lot of different applications. You need at least hourly data. And you can't have an observer going out every hour unless they're at an airport and there's someone manning it and can check the weather every hour. And so weather stations that are automated are used for high frequency data a lot. And we find that this is really, really necessary. But, and there have been a lot of, there's some engineers on campus here that have been developing some very, very simple automated methods for measuring temperature and rainfall and humidity and solar radiation and things like that. But they all have their own quirks and their own problems. And so you have to decide which one you want. You know, do you want stability over time? Do you want quality? Do you need speed, uploading right away? And those are probably different instrument systems for every need. As far as different countries, most of Europe, for example, has gone automated because they don't have the money to do the manned weather stations anymore. And so more and more they're going to automated systems. And since they're using different measurement protocols, this creates blips in the climate record, because there could be biases and changes in the way that, for example, a solar radiation shield, you change the shielding and all of a sudden the temperature changes during the day. So there's a lot of other complications here. And technology can help, but it's not the complete answer to the problem. Corvallis is actually a new network, started in the late 90s. And there's no way that anyone would ever fund a network of that density electronically. No one would pay for it. And so they've gotten together a lot of volunteers to make it work. So there's a lot of room today still for citizen science to be involved in this, and I think that will continue to be the case.
And then I have another question about, like, reimbursing for abnormal weather conditions. How do you go in areas where basically abnormal becomes normal? When you look like in the South San Francisco Bay Area, like Mountain View, where it has not rained for like 3 years, or where it constantly gets warmer, do you then say, well, the climate is going in the same bad direction anyway, so therefore the bad direction is now normal and you don't get anything.
Yeah. So as the climate is changing, the normal changes. It's really what you're saying. We'll call it a non.
Then what is normal when it was like not raining for 3 years, you get reimbursed. So if it doesn't rain the 4th year, then not raining was normal the past 3 years. So you don't get any reimbursement anymore because not raining has been normal now.
Yeah, well, we try to look at longer time periods than that. I think there's no doubt that Californians are still getting paid. They're getting paid often for blended planting where they can't plant because they have no agricultural water available. They have no irrigation water, for example. And the RMA takes those into account as well. So they're still getting paid. We try to keep the last 30 years or so moving along. So as climate changes, that normal also changes. But we do look over a multi-year period that's longer than just 3 or 4 years.
Chris, there's one on that.
Hi. So fantastic talk, and obviously very instructive in the sense that you are swimming in data. You have a quantitative model. You have a unified, as far as I can tell, a unified architecture where all the data is kind of consolidated very straightforwardly in a single place. And moreover, the people who are consumers of your data, the public, they kind of are used to making, they're used to the scientific community making predictions that they weigh in on. I mean, weather forecasting has been around for a long time. Yeah. So do you have any comments about how the lessons learned from in areas where there is less quantitative data, in the medical community, for example, there's the kind of problems that we face in biomedicine are often lack of consolidation. So the work in ontologies is often trying to develop standards that where people can agree on the terminology. And you guys don't have that problem so much, but we certainly do. And yet, because you have excellent instrumentation and a wide coverage and relevancy, you know, those things get handled straightforwardly. So do you have any kind of commentary or thoughts about, you know, what we should be doing as a community to try and globalize our representations, to kind of really pipeline the data in such a way that would then make it practically useful so that we can make predictions? So, for example, there's cancer reporting, is a very well developed.
Which reporting? I'm sorry.
Cancer reporting. So the demographic reporting of cancer statistics, for example, is something that is fairly well developed across the United States. But even that has fairly, it's kind of sporadic in many places. I think I remember seeing that there's not universal coverage across all states for this. It's in pockets. And so, you know, is there other parallels that we can, where we should be paying our attention to in the conversation about medical and biomedical data, that pointing to climate data and pointing to your work, we could use as a sparring point? It's like, these guys have got this infrastructure set up in such a way that really works. This is what we'd like to do for cancer reporting or for, you know, information from the literature, stuff like that.
Right. Boy, I think I'm fortunate in that meteorology has gone about naming things for a long time. And there is an organization called the World Meteorological Organization, the WMO, and also the American Meteorological Society here in this country. And we have very well-defined glossaries of terms. I think this is what you're getting at. So even defining a cloud, it's all Latin. You know, it's all altocumulus, stratocumulus, stratus, nimbus, cirrus. You know, these are all clouds that have very specific quantitative descriptions. And as a meteorologist, we were trained to be able to determine what type of cloud was out there, for example. And when we use a term like a cold front or a warm front or a occluded front or a kadiabatic wind or whatever it is, these are all well-defined in glossaries of terms long before I ever was born. So I think I've early in my career, I was working in ecology, and I found meteorology a whole lot more straightforward. You know, it's just everything was defined. You know, it was well defined. I think where we start jumping off into the mess is how are things measured, because they're measured in a variety of ways with different biases, different instruments, different siting of stations. What kind of site does the station represent? And I've done what I can do with PRISM to try to isolate stations with similar physiographic positions, but simply have an overhanging branch on a rain gauge can reduce that precip catch by 20% and bias it. So we have a problem in collecting the data in a consistent way. And I think one of the advantages of PRISM is that we spend so much time bringing in networks that measure the same quantities in different ways and try to bring it into a seamless whole, which is a big challenge. So I think the terminology I think is pretty much nailed down. It's how we get the data.
Right. And one more thing, have you looked into the use of deep networks in OCR machine reading techniques to look at your handwritten forms?
I've not. No, I don't know much about it.
There have recently been some developments that I can talk to you about later that might actually automate the process that you're working on.
That'd be wonderful. Thank you.
Oh, any more questions? If not, let's thank Chris one more time for an excellent talk. And Chris will be around here, I believe, until lunch. And feel free to talk to him and engage and tell him more about your ontology work and how we can build some bridges here. But we should be back in 15 minutes, let's say at 10:40. Thanks.